And so we are also lucky because the TNG team came also with 2 cameras. So all the presentations are currently recorded and we will blog about them tomorrow. So yeah, thanks to the technical, what's the name again? Yeah. Thanks a lot, Gerard, for this perfect setup. Alright, let's go.
Martin will start, so we have to wait for him to get
So yeah, don't forget to tweet. I saw 2 or 3 good selfies, but I'm sure that you can do better than that. So I told you, be innovative or do whatever you want. Do the coolest thing. Do we have professional selfie here?
Yeah.
Like people who do it like every day. You know? Okay. I confess I am a professional selfie, yes. Ready, Martin? You're here?
I'm ready.
Okay, let's start again.
Thank you. Yeah, hello. Before we start with our program, just a few words. We want to introduce ourselves. So we are from the TNG Technology Consulting Company. This is Thomas, this is Julian, and my name is Martin. Yeah. TNG Technology Consulting is a company based in Unterföhring, and it's specialized on high-end IT consulting. And it's a partnership based on, it was established in 2001, in the year 2001. It was the winner of Bayern's Best 50 in 2010 and 2012. We are about 140 permanent employees, where 98% have a university degree. And what's very special for TNG is every second and every fourth Friday we have a so-called Tech Day. And this means for us we have time for some internal activity, for self-improvement, or to build cool stuff like this cube. And we want to speak about this special cube. Okay, the doorbell is ringing. We have projects together with up to 30 TNG employees and best practices, agile development methods, and much more. This is what TNG stands for. If you're interested, send your application to worktng.com. Currently we are searching especially Java developers. Okay. And now the interesting part. Oh. What's wrong? Okay. We want to show you the 360-degree camera. Once in a year, we have a retreat. It's the so-called winter retreat, and the colleagues gather together, and they want to find some topics they want to speak about. For example, they want to speak about the newest agile technology, the newest programming language, or whatever. But we didn't want to talk. We wanted to make something cool, this 360-degree camera. So we were about, I would say, 8 colleagues, with the goal to build this thing. And when we have a look to the agenda, at first we want to introduce you to the idea, then we want to tell you how we realized this project, and a short conclusion. So, Thomas, it's your turn.
Yeah, I'll start with the most classic thing you'll ever see in this presentation, and this is the panorama picture. Is the microphone on? Yeah, okay. So panoramic pictures are something that's really as old as photography itself. The first panoramic pictures were taken in the early 19th century, and what you basically do is you just take some photos, you cut them where they overlap, and then you glue them together. These kind of pictures got more popular when smartphones came up and new camera technologies came up, and nowadays you can take them with and it's nothing special anymore. But the normal panoramic picture is just 360 degrees in one direction, and the other direction we got 180 degrees, and normally you don't cover them. So what we wanted to do was to take this a little further and get the remaining 180 degrees also. So basically this imposes us on some problems, because one thing is you'll have to take a lot of pictures to get all the spherical radius covered. And what you can do, you could of course take a lot of pictures and then just put them together. But as we did in our experiment, is that we just took one picture from a lot of cameras, and this is a much easier approach, I would say, because we don't have some effects that would otherwise be a little bit difficult. When you get the pictures, you have to put them together, and this can be done with some techniques which we'll see later on. And when you finally got a complete picture of all the cameras that are in there, you can project them in different ways. So one way would be just to put them in one big picture and just display them all together. But this is a little bit boring on the one side and a little bit unusual on the other hand, because you would see distorted pictures, and this is not what you really want. You could also project them on a cube, on a sphere, and then just show this one, and this is called a little planet. This is what you see here. So it always looks as if someone will in a moment put a little prince on it. So it's really a nice thing. But you can also take it and use it to move around within the picture. So this is a third thing you can do. Okay, let's get to other projects that were invented before we got the idea. So the first one is the panorama camera. I think it's the most important panoramic picture that is not currently on the market, but will hit the market soon. It is a diploma thesis in the first place by Jonas Pfeil, sorry. And after he finished his thesis, he got crowdfunding at Indiegogo, so he got 1.25 million US dollars, quite a lot for a crowdfunding. And with this money in the back, he could implement this camera. So what is the camera basically about? It's 11 centimeters in diameter. It has a weight of 300 grams, so it's not very heavy, and it has 36 cameras built in here and also on the other half of the cube. And when you put all the pictures together, you get a total picture of 72 megapixels, so this is a lot. The special thing, and this is why we need the foam out here, is that it can be thrown. So normally you would throw it up, then at the highest point it will take its picture, it will stitch it together, put it together, and then you can catch it again, or if you don't catch it, maybe it won't break, but this is not true. Okay, and here's a typical picture of what you see. So you always have one guy down there who is trying to catch it very eagerly, and there's also other guys, and what we can't see here is the other half of the picture. So this is only one half of the whole picture, because on the other half you would only see sky, and this was not important for this picture. Okay, next one. This is the project done by Jonas Ginter, who I recently met at the Maker Fair in Hanover. And what he did was he put together 6 GoPro Hero cameras, which are quite cheap. And these cameras have a wide angle lens, so nearly 180 degrees. And with 6 of them you can cover the whole scene. And he just made some videos with it, and afterwards he stitched every picture together, and when he was finished with that, he put it on such a little planet as we saw before, and he got a really nice view of him driving around Berlin, which we'll see here. Oh, what a pity. I'll try again. Normally it would work. Oops. Yeah. So he's driving on this little planet. And this is really cool. Okay. Let's get to the next project. This is a Munich-based company. It's the Virtual Surfers. They drive around with their car on which they have mounted a 360-degree camera, and with this camera they can do films like Jonas Ginter did, but they use it in quite a different way, because here you can see the car driving around Munich. It's just a normal YouTube video, nothing special about it, but wait, if I put my mouse in there, I can move around the scenery, and I can watch the sky, I can also see that this is their camera, and this is something that will be done in documentaries soon. So the first 3D documentaries are on their way. You can then just look around the scene and you can see what you want to see, and this is something that will soon be not really standard, but we'll see it a lot in a few months, I would say. Okay. So enough for the other projects. Now let's get to our project. As you can see on this picture, this is our camera, which we built using within the winter retreat. We then used some tech days to improve it, so at first everything wasn't that fixed within the cube, and it would be hard to throw it up if it isn't fixed. So we got 12 cameras in total. Every camera has around 100 degrees field of view, and the camera resolution is about 2,500 pixels cross 1,600 for each of the cameras. With that we can cover the whole sphere, and it's quite good, I think. Here is some picture we took. This is 110 degrees in the vertical direction, I would say, and 360 degrees in the horizontal direction. So whenever you build such a thing, the first thing you'll ask is, why the hell are you doing this? At first, our main objective was, all the cameras you saw today, they are not freely available by now. So we wanted to have one, but we couldn't buy one, so we had to build one. Another main objective was just to understand the technique behind it, to see if we could improve something about it, and to see how everything works on the inside. And this is a thing that we really wanted to do, and we had fun doing it in the end. And also it covers a lot of areas in the technological field, so we could really experiment with a lot of different things and try out things that we couldn't before. So this was really fun, and at least we got something that was really, really close to the fraternity cube of Portland. Okay, now Martin will talk about the concept.
Yeah, okay, thank you Thomas for the introduction, and now we want to speak about the concept. At first we had to think about, okay, how can we realize such a panorama camera? it was clear to us that we need cameras. Not only one, not only two, we need a bunch of it. But there was one prerequisite. We only wanted to use off-the-shelf hardware. This means we wanted to buy a small mainboard CPUs and stuff, computers, which you can buy on, let's say, Amazon or Conrad or whatever. And as Thomas told us, normally the cameras have a field of view, let's say, about 50 to 60 degrees. And for us it was clear that we have to use somehow fisheye lenses so that you have a wide angle lens. Okay, in this case our concept was we need about 12 cameras if we have a field of view of let's say about 100 degrees. 12 cameras. And of course we need a central computer which is capable to gather all this image data and to stitch it together to one whole image. Normally our concept was to create a camera which is capable or which has not that much weight that you can throw it in the air and at the highest point it should trigger and release and make a photo. But if you have a nearer look to the PanoCube, it's maybe a little bit, not that easy to throw and catch. So we've decided to implement an Android app, and this Android app is able to trigger the PanoCube using a wireless connection. And all those the central unit, the main board has wireless LAN too, and so that the data communication is there too. Okay, now we want to speak about the realization, and let's have a look to the concept again. The cameras. We've decided for the Raspberry Pi because you know it's easy to learn and it's off-the-shelf hardware. And there are cameras available for this. And for the central unit, we've just decided for the Ultracode U3 because it has much more process power than those Raspberries, for example. The Ultracode has about, I would say, 2 gigahertz. You can do this with Intel Galileo Board 2, we think, but at this point in time when we've built this cube, it wasn't available because not published yet. But now it's available and we think you can do this with the Intel Galileo Board 2. And maybe an advantage is that you have a PCI Express slot, so you can maybe create a board for this and connect all the cameras directly to the board. Because if you have a nearer look onto this, we have to build in 12 Raspberry Pis. And yes, it's not the best solution, but it was the easiest for us because we only had 1 day winter retreat. Okay, to don't mess up with cables and stuff in the PanoCube, we've decided to use wireless connections. So we've just added wireless sticks onto the Raspberry Pis so that we were able to make all the data communication without cables inside the cube. Okay, and now, Julian, it's your turn. We have a nearer look into the cube.
Well, thank you, Martin. First question is, why did we build a cube to host all those cameras? The thing is, if you take 12 cameras and all the computers and throw it on a pile, you don't have a panoramic camera, you have a pile of computers. So we decided to have some casing for our camera. And we are software engineers, we're not really craftsmen, not really handy, not really great at using power tools. It's rather adventurous seeing us using power tools. And so we chose some structure that's easy to build, so we chose a cube. Mostly it consists of planes and 90-degree angles, so it's easy to build. And plus, the faces and the corners are evenly spaced, so those are the points where we place the cameras later on. It's easy to mount the cameras, and if you leave one side open of the cube, you have a huge access opening to work around with your hands in it. So yeah, it's mostly the decision we built something that's easy to build. Yeah. Another thing is the cameras. We bought the off-the-shelf Raspberry Pi cameras, which come with optics that have about 60-degree field of view. And we knew we need more field of view, so we bought some custom lenses for it. But the thing is, we also had to glue the mount for the for optics onto the sensor and everything. And we do it by hand and everything, so it's not really optimized, no optimization between the sensor and the lens. So actually the lens we bought should have a field of view of 170 degrees, but since the sensor is not large enough for the optics, we only get about 100 degrees field of view out of it. Also, it's not really clean work that some of the cameras have real big distortions on the edges of the image. We come to it later on. Here you see everything that's placed inside the camera that's going around. It's nearly the Pi I was speaking of, so if these are 12 microcomputers with the camera where we connect the cameras to. This is our central computer where we stitch the image together and with which the Android app is communicating. We have a wireless access point inside the device, so this cube actually opens its own wireless network which you can connect your phone to. The actual cube itself with the cameras already glued hard into it, which might not have been the smartest choice. And the thing we didn't talk about is the power supply, which is a big problem for us because, well, as I said, we have 12 computers plus the central computer plus the wireless access point, and all of them need to be powered. So we're using 5 battery packs, which are usually used for charging mobile phones. Each of them have a capacity of, I think, 15 ampere hours, so they're really large and they provide 3 amperes of power. And they're really heavy, and 5 of them are placed inside the cube, which is one way. We don't want to throw them up in the air. And also, as you see, all of the stuff lying on the table needs to fit in the cube, which is not that easy. Plus some cables you don't see in the picture. And we just see a slideshow of mounting together all the stuff in the PanoCam. So we start off with an empty cube with the cameras mounted, and then we start adding the computers and connect the cameras to, which is quite a delicate task because we can damage the cables with the cameras quite easily, as we've seen today. And we're preparing for the talk. We start adding all the other components. Now we have, I think, 10 computers already inside, and we need 2 more. And once we add them, you see there's not really a lot of space left. Maybe you could optimize a little bit, but not really. And then the last step is you need to add the power supply. Once we added this, I think the cube is pretty full. And the thing, it pays off that we chose the cube because we have this large opening where we can put everything in and fumble around. So much for the hardware, and now Thomas is going to tell you a little bit more about the software inside.
Yeah, thanks a lot. Now we'll get to something we'll get back to something we know about, and this is the software part of it. The first thing we'll have to do is to provision the device. So we'll have to install software on it so that we can run the software we need to run to stitch the image together in the end. And normally what you would do, we have Linux inside each of these devices, and it's Ubuntu. So basically what you would like to do is apt-get install, all the stuff you need. And yeah, he'll do this on 12 devices and he'll finally get to hell. Because you miss one step on one single device and everything is going to fuck up when you least need it. So this is really something we want to avoid. So in our case we used Ansible. Provisioning is something that was, let's say there are provisioning tools for a few years by now, but the most popular is still Puppet, which is Ruby based and pull based, because so we have to install client software on each of these devices. This client software then pulls for the software that needs to be installed, and when it has done this, it finally installs it. Chef is something very similar. It's also Ruby based and pull based, and we didn't want this because we just wanted to install it using the normal SSH connection, and for this we needed something that's push based, and with Ansible we finally found something suitable for this case and just used this one. Ansible is pretty much the newest tool available, so it's the new kid on the block, but it's pretty cool already, I think. So let's have a look at Ansible itself. Since it's push-based, we need something to declare these are our hosts and these machines need to be provisioned. And this can be done using a simple inventory definition file. What you can see here is just, we have some groups. It's just an ini file. So we have the cam group containing all the cameras, and we have the Odroid group containing the Odroids, the central computer in the middle. Yeah, what you normally have to do is, if these are not DNS names, you need to add them to your etc hosts file or to your SSH config, and then everything's fine. If you have something different than port 22 for your connection, you can also reconfigure this in this inventory definition file. Okay, now let's get to the part where you have to decide what to install, and this is done using so-called playbooks in Ansible. The first thing that comes to your mind when I talk about playbooks is this one. You're not alone. But if you think about it for a little while, everything that comes with playbooks is about provisioning. So that's just another form of it. Okay. So playbook is just a plan for provisioning your software onto your device, and it's not as verbose as it is with Puppet. It's done in YAML, so it's really a small device, and it's not declarative. In this case, it's just procedural, so everything is done task by task. Let's have a look at a sample playbook. This is actually a part of our own file. So basically, what we do here is we provision the cameras. We use this. We do this as a super user, so sudo is true. And now we can just go through all of the tasks. So in this case, we're using a line in file. We use this line in the etc hosts file. Then we copy something from the inventory directory, which is on the server machine. That's the inventory build. And the reconnect sh file is copied to the client machine to use it in reconnect sh using mode, using executable mode. And the next thing we do is we just install some software on it using apt. And in this case, we're installing it because we stay present. And all the items here are these ones, where in the with items section. And then there's the last thing, we need to periodically execute the reconnect script we just copied, and this is done using this line of file. So basically, that's, let's say, half of our configuration. And with these little lines of files, we can do everything that we need. So this is something that's really, really cool, I think. Okay, but maybe I'm wrong. Okay, when it comes to the command line itself, you have to then execute some script to finally provision everything on the device. So these are two commands that we use. The Ansible command itself, which we can use to ping something using a user and executing it as a super user, for example. And if you want to provision a playbook, a complete playbook, we use the Ansible playbook command. We can then define the inventory definition file, the playbook itself, and we can limit the devices. So maybe we just want to provision the cams and leave out the central computer, for example. Okay, and that's about it for provisioning. Next thing I want to talk about, for just a little while, is the data transfer section. For this, we use the Python Twisted framework, which is just a small framework for asynchronous communication. We use it on the server side, so on the central computer within the cube, and on every single computer, CAN computer. And just a few slides for this. Here we can see what we do here is just we use the main method to listen to some port, and we define a factory which is then called whenever we need a new connection. So the build protocol method is called whenever we need it, and then we can just use this code to be called whenever there's a line received, or when we need to send a command, we just write to the transport protocol when the connection is made. This method is called, and when the connection is lost, we can call this method. And that's about it for the communication framework itself. The last thing we did was implement an Android app which can be used to trigger the camera, to stitch the photos together and stuff like that. So it basically connects to the central computer and then sends some JSON files to it, for which then control the execution. So we send, please take a picture to the camera, to the central computer within the camera, and then the command is sent. The camera, the central computer itself sends some command to the client computers. These take the picture, send the picture back, and then we can stitch the pictures together. And that's about it for the software part, except for the main part, which Martin will explain, and this is the stitching process itself.
Yeah. Thank you, Thomas. Okay. After all those technical stuff, we want to speak about stitching. So, what does stitching mean? Okay, this is if you put take several pictures, images, and you put them together to one image. So normally, there it is. Okay, normally you take several pictures in a line, and then you put them to one picture together. Normally you do this when you're on vacation and you have a very nice view on something like this. Okay, what is the main problem if we are taking several pictures in a row? What is the problem? Think of it, there is a motorboat here at the lightning tower. What is the problem? If it rides from this side to this side and you are not fast enough, then you have several motorboats in the finished image. This is the so-called ghosting effect. Maybe you've heard of it. So, but the question is, do we have this problem with our panorama camera? Okay. No, why not?
Because you have all the pictures at the same time.
Right. Perfect. Okay. That's right. So you take, with this PanoCube, you take one picture at the same time, so there will not be a ghosting effect. But now we want to have a nearer look into the different stages, how to stitch images, how it works. So stage one is the registration. This means you have those several pictures and you have to find overlapping areas. And the more the images overlap, the better is the result. This is done by different algorithms, and here you can see those red lines. This is where overlapping areas were found. This is the registration. In stage 2, you're doing the calibration. Calibration means you have those different images, and you can, for example, remove vignettes. Vignettes, you have this in pictures, and it's mostly on the corners of the picture, of the images, where you have where it gets darker. Maybe you have seen this when doing photos with a DSLR camera, and you can remove this using different algorithms. And you have to go for sure that the lightness, the brightness, and the contrast is the same for all the images. In this case, we've added some different brightness and contrast so that you were able to see those different images and to see that in the calibration some distortion is added to the pictures. The reason for this is, if you make a picture which is in front of you, then you have a normal rectangle. This is this one here. But if you change your point of view, the angle changes, and then you have to distort those pictures so that it looks nice. Chromatic aberration is removed. Aberration is removed too. This is sometimes it occurs when you use low quality lenses, I would say, where the red, blue, and green color is not on the same focus. And the last step is the so-called blending. This means you have your two pictures and you put them together, and sometimes it can happen, please think about the ghosting effect, it can happen that some people or whatever, moving objects get messed up. This is the case here. And what you can do is to use masks to make it correct. But, as I told you, we don't need to do this, because we take 12 pictures at the same point in time. So, how do we realize those stitching? We've decided for Ugin or Eugene or whatever, I don't know how to pronounce it. It's an open source tool with which you can stitch images together. And it's a really, really cool and powerful software. I think it's much better than, let's say, Adobe Photoshop, panorama stitching stuff. Why do I say this? Why do I prefer to use Eugene? This is because you can script all those stuff, all those stages you can script. And this is what's really important to us. What we wanted was to make a photo, and the central computer stitches everything together using a script. And in this script, we just executed some programs like AutoPan Swift and Recalibrate and stuff. Okay, now let's have a look to the product, to the finished images. One of our first images looked like this. Isn't it nice? It was a really first shot, and if you have a nearer look on this, here we have 1, 2, 3, 4, 5, 6, 7, maybe 7 pictures. And if you have a nearer look, we have a really, really great problem with the alignment, the calibration and stuff. It looks really distorted, and no, it's not the architect's failure, it's a problem with the camera. That the building here is somehow broken. Okay, but we've improved it a little bit, and this is the next image. You see, we've just used some more pictures, and it's a little bit better. To be honest, the ground here is really unthankful because of those patterns, and maybe would be a better idea to photograph some grass. Who knows? What we've changed here was we've automated the Eugene stitching process in the script I've already told you. And we've changed the parameters we've used, because if you tell Eugene which field of view we use for each camera, for each lens, then Eugene is able to stitch it together with better quality, because Eugene knows how to distort those different images and to stitch them. So this is the next picture, and you see, it's really getting better, isn't it? There are still something missing here, because we are still not using each camera, every camera. And this is the next iteration. And yeah, we still have a problem here. And this is also due to the problem with the lenses. Those lenses are not really high quality lenses. And then we've added those fisheye lenses too. Yeah, yeah, it's a little problem. And this is one of our last photos we've taken. This was at the Big Tech Day. It happens once in a year. It's a conference from our company, and with, let's say, 400, 500 guests. And we made this photo here. You can see here's Thomas, that's me, Manuel. Julian, where are you? I can't find you. Ah, there with the laptop, gathering the data, I can see. So, and now we want to speak about improvements, Julian, I think.
I have no idea what you're talking about. I don't see anything we can improve here. Yeah, you have to see, we only have one day at a time at a winter retreat, and then we had some days, some of the tech days working on this. So we didn't spend a lot of time. We used off-the-shelf components. We have to keep this in mind when we say we have some improvements still to make. So the biggest point is the weight of the cube. The cube has been going around in the audience now, and I think you all realize it's pretty heavy. It's mostly due to the energy supply in it. Those 5 battery packs, they weigh around 2 kilograms or something. And that's way too much power, because I think the battery packs would suffice to run it for 1 day or something like that. It's mostly the current that's a problem, and maybe if you use some other different custom power supply made from lipo cells yourself, maybe you can reduce the weight a bit, or maybe if you use less computers inside. Because I think 13 computers and a wireless access point is quite a lot for one camera. Yeah, the next point is the optics. Martin has already mentioned it, the quality of the lenses, or the quality of the whole camera system itself, as we glued it together, is not really good. The lenses are not really fitted for the sensor, so we only got 100 degrees of field of view, and a lot of distortions at the edges, and problems like the center is focused, but the edges are blurred. Lots of problems like this, and maybe if you use real, not handmade optics, maybe you get better results, because the better the original pictures are, the better the stitching result will be. And if you start off with distorted pictures, you don't get too good results. Yeah, the last point is, or one of the last points, not really the last point, is you could build this smaller. So it's not really handy, it's quite hard. You can't really operate it yourself. If you try to use the trigger on your phone and hold up the camera, you're always afraid you're going to drop it, and it's going to be a mess on the floor. Yeah, so maybe we should reduce this form factor and also use a different form to compact cameras, so we can remove the fisheye lenses and move back to standard optics with 60-degree field of view, and just use more cameras and maybe approximate something like a ball, like the panorama camera, which was the original inspiration for the project. And yeah, this is actually the last point of the improvements. We said we wanted to have a camera you can throw up and take a picture in the air. for some reasons this wasn't possible. But we wanted to add a sensor like this one. It's an accelerometer with 6 axes, so it's you measure how fast you throw the ball up, and then calculate the point where the time when it reaches the highest point to take the picture. We already connected it to the computers and tested to read it out and everything, and then we came to realize we don't want to throw it, and so we left it out. But it would have been nice to use it, and it's also nice to connect more electronics to the apparatus. Yeah, well, that's it. I don't want to talk too bad about this because I think it's really good. We learned a lot about technology, we learned a lot about Python. I'm not really a Python developer. It's really nice to see the code and also see the provisioning and Ansible was a great thing because of the thing, because of all the public. And yeah, this was really nice. So this is it. Last thing to say is it wasn't only the three of us who were working on this project. Victory Tree, this was the crew working on it. And on later on the tech day we have a few people less, but still some of us working on it. Yeah, thank you for listening and if there are any questions. Thank you.
Okay, so I'm going to give the mic, then everybody can hear your question. It's kind of important.
Are the cameras truly synchronized when they're told to take the picture?
Not strictly, because the cameras tend to take the picture whenever the network connection, whenever the control command has been sent over the network connection. Sometimes it took a little bit longer, so we just got some ghosting effect in there. So this is not by now strictly synchronized, but we'll have to work on it.
What exactly did you use for the central computer and why did you need that? What was what hardware did you use?
Why do we need those?
We use the Odroid U3 computer, and why do we need a central computer?
Yes, because you could just broadcast the commands to all the Raspberry Pis or vice versa.
Yeah, at first we wanted to do the stitching process within the central computer, so that we didn't need any extra hardware to stitch it together. The Odroid was not the... It was still a bit difficult.
The Ultracode has about 2 gigahertz and I would say 2 gigabyte of RAM. And the main idea was to make all those stitching stuff on the Ultracode, because on the Raspberry it wouldn't work, because it's too slow. But we've realized that the Ultracode is not that fast too. Because one stitching process from those 12 images, from those 12 cameras, I would say it goes about 10 minutes of time, or less. 5? 5 to 10. Okay, 5 to 10. Yeah.
Yeah, it depends on the hardware. So Jonas Ginter also proposed to take something different than Eugen, because he needed about 10 minutes to stitch photos for 1 minute, and this is a factor of a great factor. So when using different software we could improve our performance, but this is not open source software, so we need to buy something, and we didn't want to do that.
And maybe it's not scriptable.
Yeah.
Do you use a broadcast message over the wireless network to synchronize all the Raspberry Pis, or do you send each of them a separate packet to start the capture?
Yeah, the process is at the moment done. All the clients register at the server, and then the server separate package to each of these devices.
So do you want to improve it to use the GPIO ports of the Raspberry Pis to get a perfect synchronization?
Yeah, we were thinking about some idea like this in the beginning, to just use the GPIO ports to trigger and everything, and then we thought we would have all those wires additionally to the power supply wiring, and yeah,
But it's
we dropped it.
one wire bus, so it's
Yeah, it would be quite simple to use it, but we thought we need to transfer the images anyway, so we already established a network connection so we can use it to take the picture.
But gathering all the image information in the end is not the time critical.
No.
But it's time critical if you want to make a photograph of a rock.
Definitely.
Something like that,
Yeah.
And have a lag time of maybe a tenth of a second.
Yeah.
So with this GPIO you can perfect synchronization.
Yes, you are.
You're totally right, but we wanted to keep things simple in the beginning.
Yeah.
Thank you.
I think there was a question.
Just one question, one more question. Would it be possible to just bypass the Ultracode and use a smartphone as the server and trigger the photos and send pictures to the smartphone to process it?
Yeah, that would be
So
possible.
that would reduce the weight of the unit?
Not by much, because the main aspect of the weight is the battery supply.
Okay.
So maybe the best choice would be to use some lithium polymer.
The Odroid has about the same size like those Raspberry Pis.
Alright.
It's really little one, credit card size, I would say. There? You got a question?
Yeah, I don't know if it was asked already, but did you plan to add something like a video or something in this direction? Because I think that would make a big value for it. Because you have the smartphone, you can do the panorama, it's fun, but if you would add video, maybe you think about it.
Would be possible, but at the moment we haven't really thought about it for a long time, because we just wanted to get the image processing done right by now, and then we could think about something like video. Jonas Ginter already said that the processing of 1 minute of video took 10 minutes of video, so this is an offline process you have to do. You have to do it offline anyway.
Yeah,
So
most processing, but theoretically you could just store a bunch of
Yeah.
photos.
So these cameras are capable of taking videos by default, so we could just send it streaming.
Okay.
Yeah.
Thanks.
Hi, very interesting project. I was thinking something similar. I'm just thinking, because of the cameras are always in the same position, would it be possible to calibrate the parameters and take the stitching much quicker by knowing where are they and the parameters?
Yeah, definitely. You're right. It would be much quicker, and but one improvement we've suggest was to put more cameras on it and to use a sphere for this. Because this is a really huge problem. If we have one camera here on this area and the next ones here at this point, this makes it really hard to make really good stitching. It would be better if this everything is on a sphere, and then those stitching time would increase.
But we made some improvements because we started to realize we can reuse the common points, because the U-turn would look at some point for overlapping sections, and then you can manually add some points, and then we realized that the points are almost the same for every picture, so we're using this data set, and this improves the quality a lot.
We could also define something about the geometry, which we haven't done by now, but this would also improve finding these common edges and then stitch it in a faster way. Yeah.
Thank you.
No more questions. Okay.
Thanks a lot.
Guys,
Thank you.